Welcome to this another video lecture. In this video lecture, we are going to discuss about the signal flow graph. So signal flow graph is basically another method to calculate the transfer function in control system. So basically signal flow graph is a graphical representation. It is a graphical representation of control system. Like block diagram method, it is also a graphical representation of control system. In this methods, in this signal flow graph, the system variables are represented by nodes. So we have system variables like input, output, the summing element, the takeoff points. These are the system variables. These are represented by nodes in signal flow graph, and the transmission function, which are the different gains, are represented by the branches. So transmission function, these are represented by the branches. And if I will take simplest of example of block diagram, like we have a input R and you're getting some output with this block C, and it is representing some system, then the signal flow graph of this single block can be represented as since there are two system variables, one is input and one is output. So I will represent these system variables with the nodes, and I will connect these input output node with a line. This represents the forward path from input terminal to the output terminal, and this system is represented by the transmission function, which can be also known as the branch in signal flow graph with the gain, overall gain. Suppose the overall gain of this system is G, so it is represented by branch having gain G. So this is how I can represent a signal flow graph in control system. Let me also represent the closed loop control system with the signal flow graph. So in closed loop control system, we have a summing element here, and we have a open loop gain G, feedback gain H, connected with the takeoff point here. C is the output, R is the input, and suppose there is it is subtracted this signal, the feedback signal, and the input is added to this. So in this case, in order to represent this closed loop control system, block diagram control system into a signal flow graph, I will represent this. Let me take the variables here. Here this summing element will be a variable, system variable. So let me represent this with the A, because it will be represented as node, and this takeoff point is also another system variable. It is also represented by again a node B. So there will be overall total 4 nodes. One is the input node R, the node A, which is summing element, the takeoff point node B, and the output terminal C. So in the signal flow graph, let me connect the input and output with a straight line. There will be an input node, there will be an output node, and apart from these two, there will be 2 more nodes. One is for summing element node A, one is for the takeoff point B. The gain between the input node and summing element is unity, because there is no gain given, and the gain between the takeoff point to the output terminal is also unity, because there is no gain given there. The gain between the summing element and the takeoff point is given, which is G, and there is a feedback which is going from terminal node B to node A, and the gain is H, but since there is a negative sign here, so we will represent it as minus H. So this will be the signal flow graph of the closed loop control system. So in this signal flow graph method, we will use some terminologies. So let me write it here, signal flow graph. Terminology. So let me take one example of signal flow graph. I'm drawing a signal flow graph here with the input terminal R, the output terminal is C, and there are different gains and different nodes are given. Suppose there are few nodes in between the input and output node with the different gain G1, G2, G3, and there are suppose feedback also given, like here we have feedback H1, here we have feedback H2, and suppose there's no feedback, but it is going from in the forward direction, and the value is G4. something like this. Okay, so to understand the signal flow graph terminology, first of all, the nodes are the system variables are represented by nodes, as already discussed. The input node is the node which is only having the outgoing branches. So the input node is always having the outgoing branches. There is no incoming branches in the input node. So this is the input node, which there is always the outgoing branches. Here no gain is given, so we'll assume that the gain between this node and this node is 1. And the output node is the node which is only having the incoming branches. So this is the output node. This is the output node which is only having the incoming branches. The path is basically the traversal of the connected branches in the direction of a particular branch. So it is a traversal, or it connects the different nodes. Now the important term here is the forward path. So basically, what exactly is the forward path? Forward path is the path which goes from the input node to the output node. It always goes from the input node to the output node. So in this example, let me take a different color here. In this example, this is the input node R and this is the output node C. What are the different paths, or you can say, if I will ask, what are the different forward paths available in this signal flow graph? So the definition of forward path, it always goes from the input node to the output node. So in this case, this path here, it goes from the input node to the output node. So this is forward path 1. If I will multiply all the gains of this forward path, then I can calculate the path gain. So what exactly is the path gain? Path gain is the multiplication of all the gain of forward path. So if I will consider this path represented by the red line, so the path gain in this case will be G1, G4, G3. So this is path 1. Now similarly, there is another path. Let me take another pen here. So there is another forward path which goes straight like this. This is also forward path. So the path gain in this case, let me write, this is the path gain, let me put it as P1. The path gain of the second forward path in this case will be G1, G2, G3. So this is how I can define the forward path. Now another terminology which we will use in this signal flow graph is the loop. So basically, what exactly is loop is? A loop is a path which originates and terminates at the same node. It is a path, let me write it here, path which starts and ends at same node. So if I'll take a marker here and represent this path here, it starts and ends at the same terminal. Okay, so if I will take this terminal here, it starts here and terminates at this same point. So this is the loop, and I can define the loop gain for this loop. The loop gain is the over multiplication of all the gains of the loop. So the loop gain for this loop, let it be represented by L1. This loop is represented by L1. So the loop gain of this loop will be H1 into G1. Similarly, there are different loops in this signal flow graph like this. This is also a loop here, which originates from this terminal and terminates at the same terminal like this. So the loop gain of this, suppose I am representing this with the L2 loop. So the loop gain of this is H2 into G3. Likewise, is there any other loop in this signal flow graph? I think there is no loop other than these two L1 and L2 loops in this signal flow graph. And the last terminology which I can describe for the signal flow graph is the non-touching loop. The non-touching loops are the loops which do not have a common node. Loops which do not have common node. So clearly these two loops L1 and L2 do not have a common node in between, so these are two non-touching loops. If the loops are having common nodes in between, they are not non-touching loops. So these are some terminologies which we use in a signal flow graph method. I hope you understand this. Now, by using all these parameters, we can determine the transfer function by using signal flow graph using a formula known as Mason's gain formula. So let me write the Mason's gain formula. The transfer function or overall transfer function of a control system or a gain of control system can be given by summation Pk delta k divided by delta. Let me define these terms. First of all, let us expand this. So this can be also written as P1 delta 1 plus P2 delta 2 plus up to Pk delta k divided by delta, where P1, or you can say more precisely Pk, is the path gain of kth forward path, which I already discussed in the previous slide, and delta is 1 minus, it is the sum of loop gain of all the individual loops. So I already discussed what is the loop gain of individual loops in the previous slide, plus this is the sum of gain product of two non-touching loops. Non-touching loops already discussed in the previous slide, minus it is the sum of gain product of three non-touching loops. So we will discuss this, plus and so on. So first of all, the individual loop gain, then two non-touching loops, and three non-touching loops, then four non-touching loops, and so on. So we can determine the value of delta. We will take one example to understand how we can determine the value of delta. And finally, this value delta k is, we can write as delta k is it is actually the value of delta obtained by removing all the loop touching the kth forward path. So we will take one example or a couple of examples of signal flow graph to understand how can we calculate the transfer function by first determining these values, path gain of the forward path, the individual loop gains, the sum of gain product of two non-touching loops, and the value of how to determine the value of delta k also.